the quiz, and you got the worksheet for this week. All right, I'm going to share my screen and guide you through what you need to do for this chapter, for this lab. All right. This is the electric field lab, which is the third lab on the manual, but we're going with this schedule, as you remember. This is the first lab that we didn't do much with. The first one was the introduction, then electric charge, and the second lab on the manual is basic circuits, but we're going to the third one first and then go back to the second one. So this is lab 3. Electric fields. And if you control click on this, it takes you to the data video that is in, let me turn that on. The instructor explains how to set up this experiment and how to do the lab. I'm going to explain what it is. You see, this is the board, and on the other side of the board, there are some electrodes that looks like this here. I'm going to show you. See here, there are 2 dots basically that are connected directly to these 2. So the instructor is actually applying a voltage across these 2, which is basically across these 2 points. Like this, she's doing it right now, but then you see when you do that, basically there is a potential 0 potential here, 10 volt here, but then there is a current going through this, and that creates a current field, and then that creates a potential field. Means at each point you have some potential value that goes from 0 to 10. So at any point on this plane, you have some value for the potential. And we are going to find all the points that have the same potential. We call them equipotential points. And now let's see, she's doing the setup. So she connects basically to these 2, which are directly connected to those 2 points that you saw on the other side. And what happens here, just a moment, I go to this is the setup. This is the device that you saw. There's a potential difference from power supply, 10 volts connected to both sides. So this is low potential and high potential, negative and positive. And then there will be a voltmeter connected to one side and this one that can be moved around. All right, so the voltmeter actually measures the potential difference between this low potential, and this point. And then she looks around, and later on you will see in the video, she looks around and finds all the points that have, for example, potential of 2 volts, and then finds all the points that have potential of, not all, I mean, she marks enough points so that she sees the pattern. And all the points that have potential 3 volts, 4, 5, 6, 7, 8 volts. And we call those equipotential lines. And you can just watch the video and see how she does that. So it's even when it is contacted to the middle, to the bottom, there's a point in here that you can put a dot showing that point has a potential difference between the other side of such a like 2 volt or 3 volts. You see that here as as she moves from this side to the other side, goes from 0 volt and then moves along. This increases 3, 4, 5, 6, 7, 8, 9, and about 10 volts here, 9.92, right? So the potential changes from here to here. All right. She's talking about uncertainties that we are not going to use, so don't worry about that. I don't know. We don't talk about that because we're not going to use it in the lab. So now she's marking, you see, a point that is about 2 volts. I don't know why she's not very careful. So 2.07, around 2 volts, 2.078 or something. Less than 2.1, I think she's happy. And more than 1.9, she's happy with it. So she's just marking a lot of points with the same potential. You see here at the bottom, she shows 2 volt, 3, 4, 5, 6, 7, and 8. And in this one, in this pattern, we have 2 parallel line electrodes. And these are equipotential lines. All right. And then this is another pattern. These are all the 2 volt points. And this is all 3 volts. They do this so fast, it's hard to see. If you want to see better what's going on, you can change the playback speed to 0.25 so you can see better. See, these are all 8 volt points she's trying to find now. And now, after finding enough points so that we see how it works, we connect the dots so you can see the potential equipotential lines. This is the 2 volt equipotential. This is 8 volt equipotential. This is 5 volt equipotential. Usually it's right through the middle. This is 6 volts. This is 3 volts. This is 7 volts. And this is 4 volts. So you see, it starts from 2 to 8 with the steps of 1 volt it goes up. So here you see that it is basically dots, negative, positive side. And this is how the potentials change from one point to the other.
Rebecca, in that video, if you can pause it. So did that say when she marked it, did she mark it from 0 volts to 10 volts, or were they both 0 volts?
No, she doesn't go 0. 0 will be right at the electrode.
Got
right?
it.
But then she goes from 2 to 8.
Understood. No, I was talking about the marking she made earlier. If you can rewind the video where she was marking the negative and positive charges. It wasn't too far back. It was briefly, maybe like 20, 30 seconds.
In here.
Yeah, it was in this pattern, but she already finished it. It was when she was using that stencil.
Yeah, I'm going forward now. Let's see. You mean this?
Yes.
Yeah, so you see, this is the negative electrode, this is positive electrode.
I see. And then she marked it with value. So is that 10 volts and 0 volts?
Oh, yeah, 0 volt and 10 volt, yes.
Understood. Thank you.
Yeah, the 0 volt is here, the 2 volt will be all these points, and 10 volt is here, 8 volt will be a little bit farther away, and so forth. Yeah. All right. Thanks for asking questions. All right, next one, you see, she doesn't show what pattern it is. So she doesn't want to get biased by the pattern. She just looks for the equipotential lines. And you see that this is the way it works. These are all 5 volts. Now we're looking at 6 volts. Excuse me. This is all at 7 volts. Oh, this is 6 volts. 7 volt is right around here. These are 7 volt points. And now she's doing 8 volts. And then I think she's doing a 1 volt line too. Yeah, okay. All right. Now she's going to draw the lines again. 8 volt. This is 5 volt, 2 volt, 3, and 6. 4, and 1. This is 7 volts. All right. And the pattern for this is a dot and a line. And that creates this kind of pattern. All right, this is 0 volt and 10 volts. All right. And then there's another one. Let me make this normal speed so it goes faster. So in this one, it's a little bit confusing, strange. And it shows 0 volts at that point. You see, at that point, it shows 0. And why is it 0? I will explain why it is 0. You see, as soon as you go to that region, it shows 0. And then there is another region here that seems to be repelling the equipotential lines. These are 8 volt points. These are, I guess, 1 volt points. All right, so she draws these. It's in negative and positive, but there are 2 regions over there that caused these distortions. Yeah, see in here, every point in that region shows 0 volt. And it is not, in fact, 0 volt. I will explain why it shows 0. And every point in here shows 4.69 volts. The reason is that, you see, this is the dot and line, and this is the last one. All right. What happens here, there is a non-conductor insulator in here and a conductor here. The plate itself is a conductor. It conducts, but not very perfectly. So that's why it shows different potential values, different places. But here is perfect conductor. And in perfect conductor, potential is the same everywhere. That's what you learn in potential. I'm going to explain that. And in here, why do we get 0 here? The reason we get 0, not that doesn't mean that the potential is 0, because we are using a voltmeter to measure the potential. And the voltmeter needs a current to read the potential. But there's no current here because this part is insulator. And so if there's no current, the voltmeter shows 0 volt, but that's not correct. Okay, that's the reason we get that. And okay, that's the video. So basically, she created these patterns that I put at the end of this video. This was one of them. This was the other one. This was the third one. And this was the last one. Okay, this is what she created. And now what we want you to do is to, for each one of these patterns, you choose 2 points, A and B, on one of these equipotential lines, not on the first one and not on the last one. And we want you to calculate the electric field intensity and at that point and direction. So for each one, 2 points. So you have a table here, say pattern 1, point A, point B, pattern 2, point A, point B, and so forth, okay? And I'm going to explain how you calculate this. And this is the procedure for that, for you to do that. And here it's talking about field lines. We also want you to draw field lines on equipotential lines. In order to understand this, I'm going to talk to you about equipotentials. So that is from chapter 24, where I teach, for example, in a couple of weeks, we get to this. This is the definition of electric potential. The potential difference between A and B, 2 points, is equal to VB minus VA, which is defined by this expression. Integral from A to B of E dot ds with a negative sign in front. The negative sign is technical. Don't worry about that right now. So basically, again, the integral from A to B E dot ds means that from A to B, you go along a path C, and along the path, you take a step del ds, and you calculate E at that point, dot ds, which is in this case, for example, ds is this way, E is this way, you get a negative number in here. And then you add all these numbers until you get to B. That gives you the potential difference between A and B, all right? And then if the 2 points are close to each other, you can say E is pretty much constant, and delta V becomes negative E dot delta S. But in magnitude, delta V becomes just E times delta S. So I usually ask this question. If you think about it, it is very more understandable than if I tell you, how can we have 2 points fairly close to each other that have exactly the same electric potential? So we want 2 points, means delta S, from one point to the other, close to each other, and they have the same potential, means delta S is not 0, but delta V is 0. Can you imagine how the 2 points should be situated, in which situation, so that delta S is not 0? You take a step, short step, but you take a step. Delta S is small, but not 0. But delta V is exactly 0. How is it possible? Mathematically.
Wouldn't delta S have to be really small? Actually,
Yeah, delta S is
it's like a
small, but it's
like
not zero.
Is that possible?
And you have,
Because negative E is constant, right? So the electric field is constant and delta S isn't zero, but delta V
yeah,
is equal to zero.
yes. Delta S is non-zero, but delta V is zero. How is that possible? Can you imagine two vectors, E and delta S, whose dot product is zero?
Well, yes, you can, but delta S has to be zero. But since it's not zero, then I cannot imagine it.
Okay. You need to review the dot product. What is the dot product of two vectors?
Isn't it the same dot, like the same vectors will cancel out if it's dot product?
What do you mean same vectors cancel out? I don't get that. Say that again. Rephrase that maybe.
If I remember correctly, for dot product, if it's like um vector A dot vector A will equal to
Oh,
0. That's how I.
no, no, that A cross A is zero. The A dot
Oh,
A is not zero.
okay, then I
Wouldn't
forgot.
because isn't dot product supposed to be technically so the x coordinate time the x coordinate of E times x coordinate of delta S
Yeah,
and then
that's Cartesian.
plus the y coordinate of E
That's right. So yeah, you say A dot B is equal to AX BX plus AY BY plus AZ BZ. Right? That's what you remember.
yes, that's a dot product.
From here, it's hard to tell when when the dot product is zero, because some of them can be positive, some of them can be negative, they add up to zero. So when does that happen? It's hard to tell from here, although it is a correct formula. But this is called dot product in terms of components. But we have original definition of dot product. Can anybody remember that? A dot B is magnitude of A times magnitude of B times
Cosine theta?
cosine of the angle between them, right?
Yes.
And if you have a vector here, another vector here, let's say A, and this is B, and the angle between them is phi, then A dot B can be written this way: magnitude of A, magnitude of B times cosine of angle between them. So is it possible that A and B are non-zero vector, but the A dot B is zero?
Yes, it is possible. If theta is equal to, I believe, 90 degrees, so
Yeah,
then
yes,
it'll be zero. So therefore, the A dot B would be zero.
that's right. If phi is equal to 90 degrees, cosine of 90 degrees is zero. So you can have two non-zero vectors dots to each other, and the result will be zero. So when A and B when A and B are perpendicular to each other, A dot B equals zero, right? So you can have delta S non-zero and E non-zero and get delta V equal to zero. That is when delta S is perpendicular to delta E, to E. Means that if you have electric field in space, if you move perpendicular to E, you don't change potential. The same applies to the gravitational field and gravitational potential. Remember, the gravitational field of the Earth is downward, right? But if you go horizontal, perpendicular to the field, on a plane that's perpendicular to the field, horizontal plane, the potential doesn't change, or potential energy of a mass doesn't change. Remember that from mechanics? I don't know if they are, if these things are highlighted enough in previous course. But anyway, this is the same thing. Electric potential is the same thing. All right, so there are two ways that these delta V can be zero for 2 points that are close enough, close to each other, but not the same points. So delta S is not zero, but delta V is zero. There are two ways it can happen. One is that delta S is perpendicular to E. The other thing is that electric field would be zero, right? If the electric field is zero, that will happen too. So delta V is zero when E and delta S are perpendicular to each other, or delta V is equal to zero when E is equal to zero. Each one of these have very interesting physical results. What happens if E and delta S are perpendicular to each other? So suppose E and delta S are perpendicular to each other. In an electric field, if we always move perpendicular to the direction, to the field lines, in perpendicular direction to the field lines, we move on a surface with the same electric potential. Means the electric potential from one point to the other doesn't change. So surfaces that are perpendicular to the electric field lines at all points define equipotential surfaces. So here, the field lines are to the right, equipotential is a uniform field. Equipotential surfaces are planes perpendicular to those fields. Like the gravity of the Earth is downward, equipotential surfaces are horizontal surfaces, right? Or in this case, the electric field of a point charge is radiated outward from the charge. The equipotential surfaces are spheres centered at the point charge, because the sphere is always perpendicular at the electric field line at all points, right? And this one is also perpendicular to the field lines at all points. So if you go perpendicular to the field lines, you have to move on a surface of a sphere. So in this case, equipotential surfaces are spheres. In this case, you see the electric field lines are blue. The equipotential lines have the same dashed line. What color is that? Is yellowish or no?
Orange.
Orange. Yeah, thank you. Yeah, they're orange. And you see that at any point, those equipotential surfaces are perpendicular to the electric field line. You see here, perpendicular, 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 every point. Here, here, here. At any point, every equipotential surface is perpendicular to every field line. And this is another case. See, this is the same as the dot and the line. Remember the equipotential lines you saw when you go close to the surface, it becomes like that, equipotential lines. But if you go close to the dot or the sphere, it becomes closer to the sphere. So this delta S being perpendicular to electric field, which makes delta V equal to 0, gives us equipotential surfaces. Make sense? Any questions? All right. Another way that delta V can be 0 is when electric field is 0. So far in this, the theory course, the lecture, have you talked about electric field being 0?
No.
I guess maybe not. It is, we get to that in chapter 23. All right. Electric field is 0 inside a conductor, because conductors have a lot of electrons to move. And the electrons, if their electric field is not 0, the electric field applies forces on electrons inside the conductor, and the electrons move until they get to a situation where they cancel, the electric field becomes exactly zero. They don't stop until the electric field is exactly zero. So the electric field inside the conductor is zero. That is why E field is zero inside the conductor and is perpendicular to the surface just outside. All the points in a conductor are always at the same electric potential. So a conductor defines an equipotential region. This also means that when you connect two conductors of any shape by a conducting wire, the two conductors and the conducting wire are all at the same potential. This is beside the point. We're not going to use this. But in the chapter following that, the capacitance, we are using this fact a lot. All right. So that is why, for example, if I go back to the worksheet, if you go to back to the worksheet, it says field lines are always perpendicular to equipotential lines. All right, because we are talking about two dimensions here, equipotential surfaces now become equipotential lines, which is the cross section of equipotential surfaces to this plane that we are working on. All right, field lines are always perpendicular to the equipotential lines. Field lines do not intersect one another. That is another property that we didn't talk about here. If field lines intersect with each other, because the field lines are always along the direction of the force acting on the test charge, there will be two forces on a test charge. That's not possible. Field lines are perpendicular to conductors at the surface. Again, remember we said that the surface of a conductor is an equipotential surface. So field lines should always perpendicular to the surface of conductors. This includes the conducting electrodes at 10 volt and 0 volt. Field lines are directional. We show the direction by arrows and are from higher potential toward the lower potential. Their concentration, the concentration of field lines at any point in space is proportional to the electric field intensity at that point. Lines are closer together where the field is stronger and farther apart where the field is weaker. So what we want you to do is to go to each one of these patterns, draw several field lines. Field lines are perpendicular to the surface of the conductor and perpendicular to the equipotential lines. So for example, if you want to draw a field line, you can start from anywhere and go perpendicular to this. In this case, it's very easy. Go just perpendicular across. In here also. But when you go from here, it goes like this. You see perpendicular at any point. And here, like that. And here, go perpendicular, and then it becomes like this. And here, perpendicular, like that. So you can draw several lines, and they are directional, and they are always from positive to negative. They are in the direction of the force acting on the test charge, which is positive, therefore away from positive and toward the negative. So you put arrows on them. For example, in this case, yes?
Quick question. So for the fifth portion where it says their concentration at any point in space is proportional to the electric field intensity at the point, so the lines are closer together when the field is stronger. So how do we know when the field is stronger? Like, how do we detect that? Like,
Here, you see in this pattern that I'm showing right now,
yes.
the fields, the equipotentials are closer to each other here. Actually, it also works for the equipotential, but that is talking about field lines.
Mm-hmm.
I'm going to, and here, let me go from for here, for example, the one of the field lines will be like this, right? And you see that there's less concentration of field lines here. If you just go with the same steps, there are more field lines here than here. So here, the field lines are away from each other. Here are closer to each other.
I see. Just because the concentration of the electric field is like
That's right.
spaced out. So it's like because the dots represent
Yeah.
charges of the. Okay, that makes sense.
All right, let me, if I go to these field patterns, you will see it better. You see here? So for example, here you see the field lines are closer to each other. You see the field lines are blue ones and from positive to negative, right?
Yes.
They are closer to each other, so field is stronger here, but around here, the fields are farther from each other.
Yes.
And for this one, you see close to the charge, the field lines are closer to each other. As you go away from the charge, the field lines get farther from each other. That
I
shows that.
see.
Yeah, so the concentration of the field lines shows the strength of the electric field.
Understood.
Yeah. And also the concentration of equipotential also shows the strength of the electric field. We are going to do that more quantitatively in this lab. All right, so let's say, so I would like you, I'm asking you to print these patterns and draw some lines, or if you can do it on your computer with a pen, the way I do. You see here, this is one line, perpendicular here, perpendicular everywhere, right? One line goes directly from one charge to the other, or one electrode to the other. But in here, you have to go this way, you see, perpendicular to the surface and perpendicular to the equipotentials. And then this way, and then this way, see, and then this way. The farther you go, the farther away the field lines become, because the electric field becomes weaker as you go. Of course, I didn't do that quite. So you draw some field lines like this so that you see the pattern, and they are, you put arrow on them so that you know the direction from positive to negative always. All right. And then for, so on each one of these patterns, we want to draw electric field lines. You see, for this one, it will be like this. One is going directly here, one is going directly. You want 6 or 7 field lines so that you see how it works. And for this one, it is a little bit tricky. So the field lines will be distorted. You see, this is a conductor. So it will be like that and goes to this, and then on the other side also goes to that, right? It will be like this. And sometimes it is distorted. And for this one, you don't care because it goes like this, right? Try to do some so that you understand how it works. Yeah, in this case, the field lines are distorted by these two regions. All right, and then we want you to choose 2 points, A and B. Let's say A here and B anywhere, B here, anywhere you want. But two points that are not similar to each other. And then you can preferably draw a field lines that passes through these points. This is fairly close to this one. So at point A, you want to calculate the intensity of the electric field, and also you want to calculate you want to figure out the direction of the electric field at that point. The direction is always parallel to the electric field lines or tangent to the electric field line. For example, at this point, it is tangent to this field line that passes through this point, and tangent can be this way, can be the other way, but in the direction of the line. So it will be like this. At this point, it will be like this. It is perpendicular. The field at that point is perpendicular to the equipotentials and is tangent to the field lines. All right. And then we want to find EA and EB magnitude. How do you find E, the electric field intensity, EA? So that we can do by the change in potential around that point. So let me go back to the lecture again and tell you how it works. All right, we passed these. Let's see. All right, here. You see around if the point A and B are fairly close to each other, this E doesn't change much between A and B. So you can write that delta V approximately equal to E dot integral of ds, which is E dot dl, or E dot delta S. All right, so this delta S is integral of ds between A and B that are close to each other. So let's say you have some equipotentials. This is like, let's say at 2 volts, 2 volts. This is 3 volts, this is 4 volts. And you're looking at some point here. And you can consider a field line passing through this point. And here is your point A. You can go a step here to 4 volts and a step back to 2 volts. And apply this formula. From this point to this point, 1 to 2, delta V is equal to 2 volts. And that is equal to E magnitude, because we are moving in the direction of electric field, because we're going in the direction of the electric field lines, the E dot ds becomes E times ds. So it becomes E times delta S. So the electric field intensity becomes delta V divided by delta S. Right? So delta S can be in meters, delta V is in volts. So volt per meter is another unit for electric field.
Professor, I have a question.
Yes, please.
So you were saying that we had delta V equals 2 volts because it was following the direction of the electric field lines. So in this specific example you're doing, are we saying that the positive charge is at the left and the negative is at the right then? Because
No,
if we're
it doesn't
following
matter. This negative sign, or it doesn't matter. We're not looking at direction here. We're looking at the magnitude. Okay, the direction is always from positive to negative along the line, or in the direction of the field line. If it is this way, the electric field will be this way. If it is the other way, the electric field will be the other way. If the line goes this way, it means the electric field at this point is this way. All right.
Yes.
If the line always goes from positive to negative at any point, the electric field will be in that tangent to the line in the direction of the line. All right.
Understood.
So that's the direction, but the magnitude is coming from here. The magnitude we want to find is we want to see how much voltage changes for how much change in position. So what you're going to do is to go one step back. This A or B that you choose is on one of the equipotential lines. and then you go one step back and one step forward. So you go 1 volt lower and 1 volt higher. So that this delta V is always 2. Okay. But then you measure the distance. This is delta S. You measure by ruler. You put the ruler in here and measure. For example, I may measure 4 centimeters. Delta V is 2, so E will be 2 volt divided by 4 centimeter. So it becomes 1/2 of volt per centimeter. And then I need to convert to volt per meter in SI units. So E becomes 1/2 of volt over, instead of centimeter, I can put 10 to the negative 2 meter. So I get volts per meter. And this 10 to negative 2 goes up, becomes 10 to the second, becomes 100, divided by 2 becomes 50 volt per meter. So the electric field intensity here at point A becomes 50 volts per meter, and in that direction, that is tangent to the field line or perpendicular to the equipotential line. Does it make sense? So you need to find the magnitude and direction. The magnitude is delta V over delta S if you go along the electric field direction. All right? If you move along the electric field direction or perpendicular to equipotentials roughly, you can calculate the electric field intensity at that point by delta V over delta S. And then for each one of these, you choose 2 points, and then you go to this table. You say pattern 1, 2, 3, 4. For each one, A, B, A, B. Delta V for each one is 2 volts because you go 1 volt back and 1 volt front. So delta V becomes 2 volts, and then you measure with a ruler what delta S is in centimeters. And then you calculate delta V over delta S, which is volt per centimeter. For example, I found 1/2 here or 0.5, and then convert to volt per meter, which is the standard unit. Okay.
Understood. So essentially, we're just doing what you have just showed us in that last slide.
That's right.
Okay.
And for
Understood.
2 points for each pattern. So you have 8 points. And then you draw the electric field line, the electric field vector in that point.
Understood. So when we're measuring with the ruler, right, because I just want to make sure I'm measuring right. So for example, we have to start at a point that's actually like a legitimate point at like a specific volt line, right? So for example, for the first pattern, I start at like, I put a point on the 4 volts. So I would have to measure it from 3 to 5, correct?
That's correct.
Okay, thank you.
Yeah. So yeah, for example, if you are here, sometimes it's tricky if the lines are not parallel. For example, if you want to use this point, let's say, this point, then this is at how much? That at 4 volts, you go from 3 to 5. So this go 3 perpendicular to this. Of course, it will be a curved line, but you can just measure from here to here. That's approximate anyway, so it's okay. All right. And for example, you may measure 5 centimeters, and 2 volts divided by 5 centimeters will be 2/5 or 0.4 volt per centimeter, and then convert to meter, becomes 40 volts per meter. And you see that in here, for example, if you choose a point in here, the distance is smaller, right, from here to here. So here is only 1 centimeter apart, and 2 volts becomes 2 divided by 1 becomes 2 volts per centimeter, and then convert to meter becomes 200 volts per meter. So it's a stronger electric field there because equipotentials are closer to each other. Of course, when equipotentials are closer to each other, if you draw electric field lines, electric field lines will be closer to each other at that point. So both concentration of electric field lines and electric potential, equipotential lines indicate the strength of electric field. All right. So once you do all of these for 4 patterns, 2 points, find electric field and the direction, then you're done. And convert to PDF, somehow the picture of your work and upload.
Thank you, Professor. And just a quick question for the electric field to the vector, right? It's like what you it's the same thing as showed in the last slide is we're just going to literally draw the line from that point, which
Yeah.
points an arrow, which follows the electric field lines from the positive
Yeah,
negative charge.
for
And we just
example,
label it like E sub A and then E sub B, correct?
That's right. For example,
Okay.
here, you find the magnitude of electric field that, like here, will be like about 40 volt per meter, and then the direction. You see, if you look at the field line that passes through this, it is like this, from positive to negative, right?
Yes.
So at this point, will be in this direction.
Understood. So it's essentially just following the electric field line, but it'll be,
That's
okay, thank you.
or perpendicular to equipotentials, because field lines are perpendicular to equipotentials.
Potentials. Okay, thank you.
You're welcome. Anyhow, if you have any questions, I will be happy to answer. If not, I'll see you next time.
Thank you,
Bye.
Professor.
Have a good day. Have a good night.
Okay.